Just so this one, the very first thing that you know about a molecule is, uh, I mean, how do you get this information? Like which atoms are present in a molecule? Like you don't see anything. So how do you figure out the structure of the molecule? So you do mass spectroscopy. That's the first analytical technique that you do. What that gives you, it gives you information about the number of carbon atoms. It tells you the MR of the molecule, and it tells you some information about the structure and the number of Cl and Br atoms. So yesterday we did some probability work, which was that I told you that this was it. I told you that what you do is in mass spectroscopy is you take a Cl2 molecule, you bombard it with electrons so that it ionizes. So it will either turn into a Cl2 plus 1 ion, or it might break into small fragments. And if it breaks into small fragments, I mean, the molecule will break into a Cl atom and Cl ions will be produced. So there are two types of particles in a mass spectroscope. One of them is the molecule, and the other one are the small, tiny pieces of the same molecule. So if you have a Cl2 molecule, there would be Cl atoms that would also be detected. The positive ions are turned into a beam, and the beam is deflected in a magnetic field. So there is a magnetic field, and these charged particles, if you know some physics, charged particles, they always get deflected in a magnetic field, and the deflection is inversely proportional to mass. Heavier particles would be deflected less, lighter particles would be deflected more. So by looking at the deflection, you can figure out the mass of the particles. So there would be all sorts of particles. Now, if you have a Cl2 plus 1 particle or a Cl plus 1 particle, chlorine has two isotopes. One of them is 35 and the other one is 37, which is why the mass of the particles would vary. There would be three types of molecular ions. I mean, there would be three types of Cl2 plus 1s. You would either have, it will either have a mass of 74, which means that both chlorines have a mass of 37. The probability of getting 37, a chlorine with a mass of 37 is 1/4, and the other one as 37 is also 1/4. So the probability of getting a particle with a mass of 74 is 1/16. The other Cl2 plus particle could be 72. It could have a mass of 72, slightly lighter, which is why it's going to be deflected a bit more. So it will either have, one of the Cl would be 35 and the other one would be 37. Or the first one could be 37 and the second one could be 35. So the probability of getting 35 is 3/4, 75%. And the probability of getting, I mean, we talked about the probabilities. The probabilities of each isotopes. If you have 100 particles, 75 of them are 35 and 25 of them are 37. So we calculated the probabilities of getting a Cl2 particle with a mass of 72. And the probability came out to be 6/16. And the last one was that you could have a very lighter version of Cl2 plus 1 as well, which is that both Cl atoms have a mass of 35. And that will give you, the molecular ion will have a mass of 70. So it's going to be deflected a bit more compared to the other two. So both Cl35 and Cl35, the probability is 3/4 into 3/4. That comes out to be 9/16. So the result of the mass spectroscope would look like this, that three different particles with molecular ion masses 70, 72, and 74 will be detected. These would be your molecular ion, the heaviest peaks. The heaviest peaks belong to your molecular ion. And there's going to be 70, 72, and 74. And the probabilities are that if you have 16 detections, 9 of them will have a mass of 70, 6 of them will have a mass of 72, and 1 of them. So the ratio of the percentage abundance, or the ratio of the detections, would be that you will detect 9 of these particles, 6 of these, and 1 of these. So the ratio would be 9:6:1. And there's going to be m plus 2, and m plus 4 peaks, where the plus 2 only indicated that if this is the molecular ion peak 70, that's the first one. This is 72, which is plus 2. So if this is m plus 2. And that is 74. So that is 70 and 74 have a difference of 4. So that's m plus 4. So the ratio of the heights of the molecular ion peak would be 9:6:1. And we talked about fragments as well, that you'll detect fragments. And I told you that the ratios or the heights of the molecular ion peaks has nothing to do with the heights of the fragment. Maybe there is fragmentation, maybe there is no fragmentation. So the fragment or the smaller particles would be chlorine atoms, which would be, so you'll also detect, I mean, these three, if I just quickly write this down, I mean, this one, these three are Cl2, this is Cl2 plus 1 particles. And then you have these atoms, the smaller particles that would be detected as well. So there would be detection at 35 and detection at 37 because Cl has a mass of either 35 or 37. And I told you the reason we focus on Cl atoms is because Cl's isotopes are very abundant. Other atoms, their isotopes are not abundant, so you're not going to detect a lot of variations in the masses. But when a molecule has chlorine in it, there's a lot of variation in the mass. The relative atomic mass or the relative isotopic or molecular mass would vary a lot. There would be 3 different types of masses for Cl2. And we wrote this thing that if a molecule has 1 Cl, then that particular molecule will have 2 peaks, molecular ion peaks. One would be M and the other one would be M plus 2, and the ratio of the detections would be 3:1. And vice versa, if a molecule has 2 Cls, then the molecule will have 3 different peaks, and the ratio of the peaks would be 9:6:1. So this is the first one that we did yesterday. I told you that if you have an actual molecule and it has 1 Cl, and you can extend this, you can take it up till 3 Cls or 4 Cls. I mean, you can just keep on adding the probabilities, but the calculations would become too tedious or unmanageable for us. You would need a computer for that. So if you have 1 Cl in a molecule, what will happen is the molecule will turn into an ion in the ionization chamber. It will turn into CH3Cl plus 1. Or maybe the molecule breaks down into smaller pieces. There might be a CH3 plus 1 fragment, a Cl plus 1 fragment might break off, a CH2 plus 1 fragment. So smaller pieces during the bombardment by the electrons, the whole molecule will break down into very, very tiny fragments. And lots of tiny fragments, and it will be randomly breaking down into smaller pieces. So anyways, you'll have a molecular ion, which would be the big molecular ion, the heaviest one, and then these tiny fragments. So the tiny fragments would be deflected more because they have a smaller mass. So all of these are all of these over here are your smaller fragments. Having different masses. So you would get something detection at 15, you might get something at 35, you might get some detections at a mass number of 14. So lots of random smaller detections. But we are interested in the heaviest one, which are the molecular ions. So this molecule over here will have 2 different masses. I mean, this is, so our molecular ion, which was CH3Cl, but with a positive charge, has 2 different masses. One of them is a lighter version, the other one is a heavier version. The difference between the two is that one of them has a chlorine which has a mass of 35. The other one has the other isotope where chlorine has a mass of 37. We don't care about hydrogen's isotopes or carbon's isotopes because they're very rare to begin with. So they are hardly detectable. So we don't care about their isotopes, but chlorine's isotope would be very abundant. 1/4 is the probability of getting 37. 3/4 is the probability of getting 35. So the chances of this molecular ion having a mass of 50, that's 3/4, because that's the probability of getting chlorine 35. And the chances of getting the molecular ion mass as 52 is 1/4, because that's the probability of getting Cl with a mass of 37. So you'll have, in your detections, you will have lots of tiny fragments, these ones, and then there's going to be a detection at M and M plus 2 peak, 50 and 52. And the ratio of the heights would be 3:1, which is basically 3/4 and 1/4. That's the probability that if there are 4 particles, 3 out of 4 times you're going to get 35. Chlorine would have a mass of 35. And 1 out of 4 times chlorine will have a mass of 37. Okay? Is this clear?
Yes, sir.
Okay, Bhaskar, is this clear? Asaim, is this clear?
So mostly, say,
Yeah.
in most cases, do you mean that, I mean, elements or atoms that have isotopes, they can only be detected?
Yes, you can say that. Like
Okay.
mass spectroscopy will not be very helpful for the hydrogen atom because
Okay.
the hydrogen isotopes I just showed you yesterday, that they were very rare. I mean, it does have isotopes. It does have isotopes, but I mean, the particles would be hardly detectable because there would be very few of them. So mass spectroscopy usually helps you with atoms that do have isotopes, because then the probability kicks in, and then there's a variation in masses, and you can look at the variation in masses and you can figure out how many chlorines it's got, or bromine. And we'll move towards bromine as well.
Okay, yeah.
So
I understand.
so I'm going to talk about the other one. The other thing I wrote over here in this box over here was, I told you that if a molecule has 2 CLs, it's going to have an M plus 2, and also an M plus 4 peak, and the ratio of the detections would be 9:6:1. So let's talk about this molecule. Let's say I have a molecule, and that molecule has 2 CLs. So it's got CH3 and CH2, and the last one has, let's say, 2 CLs. I mean, it could be any molecule with 2 CLs. So let's talk about the simple halogenoalkane, but it's got 2 CLs. So this molecule, if I do mass spectroscopy of this, it will first be ionized. It will turn into a beam of charged particles. And the beam of charged particle will have the molecular end, which is the big one. So it's going to have CH3, CH2, and C8Cl2 plus 1. So it has, this is the big ion, and it will break down into many, many tinier fragments. I mean, the fragmentation could happen in any way possible. The molecule would just split up into tinier pieces, smaller pieces. So there could be a CH3 fragment. There could be a CH2 fragment. There could be a Cl atom that would be flying around. There could be a CH3, CH2 plus 1 fragment. Maybe a carbon atom just breaks off, or maybe the last part, CH-Cl2 plus 1 breaks off, right? So, etc. So lots of tiny fragments, unpredictable fragments can be produced. But anyways, we're interested in the molecular ion. We're interested at the moment, we're interested in the bigger ion. We'll focus on the tinier ones later. So the heaviest one would be deflected the least, but the heaviest one will have 3 deflections. I mean, this big one over here will have 3 different deflections. Together, let's talk about the molecular ion peak. One of them would be that either both CLs have a mass of 35. So can somebody do math? It's this is 15 plus 12, 15 plus 14. What's 15 plus 14? A little bit is carbon is that's 3 carbons, 36, 39, 41, 42, and 42 add. So this is, so the carbon and hydrogens are 42, I think. So they are 42. Now the CLs would vary. Either both CLs, so there's going to be a lighter version of this. Either both CLs are 35. Can somebody just, Munir, can you double check if this is 35? So if this is 42. 12 plus 12 plus 12. Chalo, theek hai. So the mass would vary because of the CLs. So either, or you could have one of the CLs would be 37, or you could have both CLs. So there's going to be a heavier version. So can somebody tell me the masses?
116.
For which one?
The first one.
The first one.
So the first. So the other ones are like 2 lesser, right? So this is 116. That one is 114. And this one is 112, right? So the molecular ion, which was CH3, CH2, and I think CHCl2 plus. This was the molecular ion. So there are three different versions or three different masses of the molecular ion, and they've got different masses. So they've one second. So they've got different masses. So we already did this. What's the probability of getting both CLs as 37? The probability of getting both CLs as 37, we already did that. That's 1 by 16. What's the probability of getting one of the CLs as 35 and the other one is 37? That probability was also calculated. That came out to be 6 by 16. And what's the probability of getting both CLs as 35? That's 9 by 16. So we already have, and I'm going to apply the same probability to this molecule. So both CLs 37, the probability is 1 by 16. One of the CLs is 35 and the other one as 37. That is what, 6 by 16? And both CLs 35, that is 3 by 4 into 3 by 4, that's 9 by 16. So that is what I meant, that if a molecule has two CLs, then the molecular ion peaks. So this is your M peak. That one has a difference of 2, so that's M plus 2. And this one over here is M plus 4. So you're going to get 3 masses. And you're also going to get a lot of different smaller fragments. Lots of them. So lots of different tinier fragments. We don't care about them as at the moment. So what will happen is that your mass spectrum would look like this. There's going to be an M peak, there's going to be an M plus 2 peak, and there's going to be an M plus 4 peak. That's the mass to charge ratio, or simply you can refer to it as mass. And that's the percentage abundance.
Sir, the number of Cl atoms on a molecule, can they exceed 2 atoms?
I think obviously they can exceed 2, but for you it's just going to be the molecule will either have 1 or 2. Okay, so and lots of smaller fragments. There would be lots and lots of smaller randomly created fragments that are going to be detected.
Okay, sir, can you like tell me again how did we calculate the total abundance of these three?
Zaib, ye dekho na ke, we already have this information that the relative abundance of Cl has 2 isotopes, right? So the relative abundance of Cl is 75% of, like if you have a chlorine sample, 75% of the chlorine atoms would be 35, 25% of them would be 37. So the probability is 3 by 4 and this is 1 by 4. Is that clear?
Yes, sir.
Okay, so like out of every 4 atoms, 3 of them would be Cl35, 1 of them would be 37. So how did we calculate these probabilities? What's the chances of getting both Cls as 37? Well, if you know probabilities, the probability of Cl37 is 1 by 4, and the probability of getting the next one as the other one also as Cl37 is 1 by 4. So what happens when you use and, probabilities get multiplied, Cl37 and Cl37. So it's 1 by 4 into 1 by 4, that gives you 1 by 16. Is that clear?
Oh, okay. Yes, sir.
The probability of getting Cl35 is 3 by 4. And the other one is also, and the probability of getting the other one as Cl35 is also 3 by 4. So when you get and, you multiply. So Cl35 and Cl35. The molecule will have Cl35 and the other one would also be Cl35. So it's 3 by 4 into 3 by 4, that gives you 9 by 16. Is that clear?
Yes, sir.
So when you look at the percentage abundance, the molecular ion peaks would look like this. When you see a molecular ion peak like this, 9:6:1, that immediately indicates that the molecule has 2 CLs. So whenever you notice this, that clearly indicates that the molecule has 2 CLs. Has 2 Cl atoms. Anyways, now moving on, we'll also extend this to bromine now, and pretty much all the calculations would be kind of exactly the same. So now if I extend this to bromine, the only difference now is the probability of the bromine isotopes are different. And you can also get this for 3 CLs. So, I mean, although you haven't gotten any questions for 3 CLs or even for 4 CLs, but the important thing is you should be able to, like, what's the probability of getting 4 CLs with a mass of 35? That would be 3/4 into 3/4 into 3/4 into 3/4 if the molecule has 4 CLs. If a molecule has 3 CLs, what's the probability of getting the M peak? So you can extend this to 3 CL or 4 CLs, but that question would most likely not be coming in your exams. So now, anyways, let's extend this to bromine. So I'll just do the first part. I'll just do first thing, what's the probabilities of the bromine isotopes? So bromine has 2 isotopes. Bromine has an isotope which has a mass of 79, and the other one, bromine, has a mass of 81. And so the relative atomic mass of bromine is around 80. Well, the fact is there is no bromine 80. There's either 79 or there is 81. And the probabilities are equal probability, almost equal. It's 50% chances of getting bromine 79, 50% chances of getting bromine as 81. So the probability is 1/2. And this one is also 1/2. So it's 1/2. So both probabilities are basically 1/2. So I'm just going to apply this to the same, like the original thing that we did for chlorine. So I'll just copy everything here, and I'll just extend everything and apply it. And so the only thing would be that the peak heights would be different. So let's just keep things simple. I'll just so I have Br2+1 now. So that's my molecular ion, and it might break down into fragments. Like bromine atoms would be the only fragments that would be produced. And now I would have to change this. So let me just replace the CLs with BR. Just a second. So let's just focus on this one. It's so we'll have Br2+1. There's another Br2+1, slightly lighter Br2+1, getting more deflected, and there's another Br2+1. So either the lighter one, either both BRs would be 79. So it's going to be 79 plus 79. So that would give you what? That would give me 158, right? So that's going to give me 158, or it's going to be what? Either one of them would be 79 and the other one would be 81, and the probability of getting that would be what? It would be I mean, this would be 160, right? Or the third one, both of them would be 81. So it's 81 and 81, and that gives me
162.
162. So what are the probabilities of, okay, let's get rid of all of this. So let's just quickly calculate the probabilities. So getting both of them as 81, so that's half into half. So it's 1 by 2 into 1 by 2, and that gives you 1 by 4, right?
Mhm.
What's the probability of getting one of them as 79 and the other one is? So it's either the first one is 79 and the second one is 81, or, so that means plus, the first one is 81 and the second one is 70.
79.
So there are two scenarios. So this would give me 2 by 4.
Mhm. One half.
And the last one would be both of them 79. So it's what's the probability of getting 79? That's 1 by 2. And the second one is also 79. So that's 1 by 2. And that would give me 1 by 4, right?
Mhm.
And then obviously you're going to get the fragments, BR plus 1, the heavier one, 81. And this is more deflected. So that's the lighter one. That's 70. That's 79. So the ratio of the heights would kind of look like this. It's in this case, so that's the abundance. Mass to charge ratio. And so you're going to detect something at M, which is in this case 158. Then you're going to detect something at 160, which is your M plus 2. And then you're going to detect something at 162 as well, which is your M plus 4. And the ratio of the heights would be 1:2:1. So it's 1:2:1. And then you'll have smaller, tinier fragments, which we are not interested at the moment. So it's 1:2:1. I mean, that's the probability, that's the relative abundance. Like this one, detecting this particle, this BR2 plus 1, has a higher probability compared to the other two. So the middle one, that's going to be detected more. Is that clear?
Yes, sir.
Yes.
And similarly, we can also extend our rule, which we apply to. So if a molecule, so we're going to extend this rule. The only thing is that the relative detections or the relative heights of the detections would vary. So if a molecule has, so I'll just change this to if a molecule has 1 BR. So if it's got 1 BR, then the M plus 2 ratio would be 1:1, because they have equal probabilities. So if a molecule has, if you have CS3 BR and that particle is detected, then there would be two CS3 BRs basically. One would have bromine as 79, so the mass would be, what's 15 plus 79? That's what's 15 plus 79? 94.
Mhm.
94.
Or it could be BR with having a mass of isotopic mass of 81. So it's going to be 96, right? So there would be two different particles getting detected, 94, and they would have equal probability, because 50% chance of getting 79, 50% is the chance of getting 81. So you'll get two peaks and both of them would have equal height. They would have the same height. Is that clear? So
Yes, sir.
so the M plus 2 ratio would be 1:1. And if the molecule has two BRs, then the ratio of the heights would be, it would be 1:2:1. Okay, just as we, like if a molecule has two BRs, the relative detections would be The middle one has a higher probability. It's 1:2:1. Getting both 81 and getting both 79 has a lower probability.
Sir,
Yes.
the charges we're having on the ions or fragments or the molecules, they're all +1. Can't we have like +2 or any other number?
You're obviously going to have +2. You're also going to have -1s as well. Okay, the only thing is that mass
Then why aren't we
spectroscope.
considering them?
The only thing is that the mass spectroscope is tuned in a way so that it only detects +1. Because if it's +2,
Okay.
what will happen to the deflection? Would it be greater or lesser if the charge is +2? If it's +2, let's assume it's +2. Will the deflection be more or would it be less? बाज़ा क्या होगा?
Sorry, can you repeat it again? My internet is getting.
If I'm saying if the
Your voice
charge is +2, will the deflection be greater or lesser?
lesser.
+2, higher charge, there's going to be more deflection.
Sorry. Yes. Yeah, more deflection. Sorry.
So the problem would be that the deflection would be somewhere over here in this region. So your detector is not over there. So you're not actually, I mean, the जो भी system है ना, that's not detecting +2 ions. Is that clear?
Oh, okay. Yes.
And and if it's -1, it would be in the other direction. Just give me 2 minutes, okay? I'll be back in 2 minutes. Hello? Can you hear me?
Yes, sir.
Yeah. Yes, sir.
I said just 1 second. What were we talking about? We were talking about ठीक है. Bhaskar, is this point clear?
Yes, sir.
ठीक है. Negative ions will be. हाँ जी.
So, like, the detector can be placed in a way that it can like detect Cl+2 or Cl-1, right?
Hi, you can do that, but the point is we're not getting a lot of information from that.
Okay.
Sir, the where there, like the detector is tuned in a way that we're detecting only +1. We could also do the same thing for -1.
Hi, you can do that. ठीक है. But you don't obviously do that because you don't get, I mean, you don't get any extra information from that. ठीक है, is that point clear?
Yes.
So because most of the information we're getting is from the mass of the particle. So now moving on. So remember this first thing: if it's got 1 BR, if it's got 2 BR, make sure. Like I'll just show you if I can just quickly spot one question. Just 1 second. So if we can see a mass, just a second. I mean, this is one example of 9:6:1. Just a second. Like if you, 1 second, open image in new tab. So that is how it would look like, the mass spectroscopy of a molecule with 2 CLs. It's going to have, you're going to detect something at 9. I mean, these are your molecular ion peaks. The molecular ion peaks are kind of unique. They're much further away from the fragments. And you can kind of, by just looking at it, you can kind of tell that it's 9:6:1. Is that clear?
Yes, sir.
Yes, sir.
Okay, so even if you're not given the molecule, you will immediately know that it's got 2 CLs. And maybe if there's another one, if like in the case of bromine, no, I can't see any. So in the case of you forget, we'll do questions later. Now moving on. Okay, let's do carbon. How do we know the number of carbon atoms? We'll discuss that in the next class. I mean, that's the third thing in mass spectroscopy, that you can also guess the number of carbon atoms in a molecule by just looking at the mass spectroscopy. Okay, so let's do that in the next class. Okay. Okay, everyone.
Allah
Thank
Hafiz.
you.
Take care.
Thank you,
Bye.
sir. Allah Hafiz.
Hafiz.
Okay, bye.